Hello everyone, welcome to a physical science lesson. We're going to be looking at relationships, and in particular we're going to focus on graphs as a method for describing these relationships. So let's take a moment not to do some maths, but to do some good physics and chemistry by looking at the features of graphs. So here we go. When we look at graphs, we recognize they can be used to describe different relationships. And these are all the relationships that we've spoken about previously. A directly proportional relationship, a squared relationship, an inversely proportional relationship. But when we deal with graphs, there are some skills that we need. And these skills relate to the plotting of graphs, the sketching of graphs, and interpreting of graphs. Now, we're not going to be able to do all of those skills, but we're going to focus on them one at a time. So let's begin by looking at what it takes to plot a graph in physical science. And here are some points to follow. So when you're drawing a graph, one of the first things you've got to do is you're going to look at the data. That will normally be given to you in a table. And you've got to recognize within the table that there are independent variables and there are dependent variables. And you need to make sure that you understand the difference between an independent and a dependent variable. Can you remember what those differences are? Well, if you said that the independent variable is the one that you control, then you're right. The dependent variable is the change that you observe because of what you have done in an experimental situation. All the other variables are constant. They are the control variables. That's what makes it a fair test in an experiment. So be aware of what the independent and the dependent variables are. Now, when you are looking at the data, you have to decide what the heading is. The heading is usually related to your hypothesis. And it will relate your variables to each other and describe them in detail. Now, some people are quite static and they don't give much detail. They'll say something like velocity versus time. I prefer to be more descriptive in my heading, and I'll show you an example shortly. So please remember that you can earn a lot of marks and you can gain a lot of understanding from a graph if you put all the bits and pieces together. The heading is one of those. The other is that you need to label the axes. So when you label the axes, you need to make sure that there's always a unit included. So here's a sort of outline of what I've just said. For any graph, we need to recognize, mostly in science, we look at only this quadrant. So it's on this side, there are positive values, and on this side, there are positive values. And that's what we're going to be looking at in terms of the area that the graph occupies. The independent variable, with an SI unit attached to it, is the one that you would control in an experiment. And because it's the independent variable, I want you to understand it's always written on the horizontal axis. Now, I don't like to say x-axis and y-axis. That's for maths. For physical science, whether it's physics or chemistry, the horizontal axis could be the time axis, or it could be the volume axis, or it could be any of the other variables that we might want to look at. But so I refer to it as the specific one that we are dealing with. And it's important that we use the SI unit with that. There are only some exceptions to that rule, and those particularly occur with time. Sometimes instead of using seconds, we might use minutes, but we don't often use hours unless the experiment is carried over a very long time. So, if the independent variable is at the bottom, the place where you dive in, okay, the swimming pool, you dive in at this side, then this is where the deep end is. The deep end is for the dependent variable, which is on the vertical axis. Please always put the SI units there and put them in brackets so we've got it very clearly stated. So make sure you can identify the variables, and in the heading, we're going to say the heading will be described by something about the dependent variable, and then in conjunction with the independent. So we usually say dependent variable first, then the independent. Now, I know this is all quite generic and quite theoretical. Let's go and look at a practical example so you can see exactly what I'm meaning. So if we are given the idea of a graph showing the distance a person walks in a certain time interval. Now, the word distance is the output. The thing that we are measuring or controlling is the time interval. So time is the independent variable, and the distance measured in meters is the dependent variable. And so that's how we set up the graph. If you do just that in a 6 or 8 mark question, you know what? You can almost get 50% of the marks just by putting those things that I've got on this little sketch graph in place. Sometimes it's 40%, sometimes it's 50%, but we want to make sure that you get, for a graph in question, as close to 100%. So what are the other details we need to take note of? Can you think what we might need to be very careful about? I'm sure you've said something about selecting the scale. Now, unfortunately, this is an area that a lot of learners struggle with, because on a table of values, they're given a whole lot of data, and it might not even be ordered. The first thing to do when you look at your table of data is to order from either smallest to biggest or biggest to smallest. Doesn't really matter. I usually like it to go from smallest to biggest. And then you've got to decide how that's going to fit in. So you look at your graph and you say, what's my lowest value? What's my highest value? And then you've got to do some clever thinking as you look at your piece of graph paper. So your graph paper for selecting scale will be one like this, where you've got blocks and you've got lines, and you'll see these are the bigger lines, and then you've got these smaller lines that represent different units. Now, the scale on this is very evenly divided. It's every 2 seconds. So that's 2, 4, 6, 8, 10, 12, 14, 16. And you'll notice that the independent variables are measured, because we are controlling them, they are measured equally spaced apart. Now, this isn't always true. What is important, though, is that you recognize that you can't just put the numbers onto the different blocks. So you can't go 2, 5, 7, 8, 15, just because that's what the numbers in the table are. If it was 1 to 15 or 0 to 15, you're going to have to say, let's count up the number of blocks we've got. In this case, you'll see I've got 1 big block, 2 big blocks, 3, 4, 5, 6, 7, 8. Now, that's a bit of a funny one, because if I look at 8 and I say 8 multiplied by 2, that will give me 16. So I can make each big block 2, just like I've got it here. And that will allow me to fit in my numbers. But they won't be one after the other. They'll be spread out at equal spaces between them. And so my values will not be jumped together. They'll be spread out. Very important for you to know. Now, if we look at the vertical axis, we also recognize we need to have a scale here. In this case, the scale is the same for the horizontal and the vertical. It doesn't always have to be like that. But again, we've got to recognize each of the values are at regular intervals. And so 1 block here represents 2 meters, and another block represents another 2 meters. So 2 meters plus 2 meters is 4 meters. And that's how it carries on going. Now, I want you to see that in this case, we've been able to plot some points on the axis, and we're going to talk about those point plotting things. But before we get that, I want you to notice these points cover the majority of the graph. They're not constricted to a small area over here or they're off the page. We've only got a few of them. So it's very important when you choose your scale to make sure your graph doesn't look like this, with points just over here. You want to make sure they fill most of the space. So if we do that, we must make sure that we select the appropriate scale. One of the ways of doing that is to change the actual data. So sometimes the data could be very small, and instead of writing it as it's given, we can say times 10 to the 15 or times 10 to the minus 3. And I'll show you an example of exactly that as we look a little bit further. I think I missed that, but on here, there it is. I've put the distance as times 10 to the 6 because you see it's the distance a rocket moves in a time interval. Now there are two more critical points when we talk about how to draw graphs accurately that you need to take note of. And those are the idea of plotting points and the line of best fit. Let me give you some tips about plotting points here. So it's very important related to scale that you can see that you've got a certain number of blocks between here and here. In fact, there's 1, 2, 3, 4, 5. So that means that 1, 2, halfway through 2, that will be 1. So what is each small block going to be? Well, if you work it out, it's 2 divided by 5, which equals 0,4. So each of these small blocks equals 0.4. So it's 0.4, 0.8, 1.2, 1.6, and then 2. So when you come to plot a point, you mustn't guess where something is. If the reading is, for example, 1.65, well, then you must be as accurate as you can to actually put the point into place. So you always start with the value that's on the independent variable and you match it to the value given on the dependent variable. So for example, if the value that I was given was, I want to find the point that is giving me a value of 1,4 as an independent variable, and let's say 2,4 as a dependent variable. How am I going to put the 1,4 on? Well, I'm going to say it's not there. It's not there. It's halfway between those two. So I'm going to do a line up here, and it's going to go to 2,4, which is all the way up there. So it's halfway in the middle there. Don't make too big a dot, and then come across here, and you'll see that we've gone up the one block, which is 0,4. So that's why we know that this value here is 1,4, and we can put a colon there to say 2,4. And you've got to make sure every one of your points is plotted accurately. And again, I've made that dot quite big so that you can see it. But when you're doing it on graph paper with a pencil, you always plot with a pencil on the inside of the graph paper. You never use ink. You can use ink down here at the bottom, but never on the inside. The labels are all in ink, the headings in ink, but the plotting is in pencil. And make the dot as small as possible. Right. I think that helps us with plotting points. Now we're talking about the line of best fit. And if you look at this line, you'll see it doesn't actually look too straight. Here's the temptation, is that some people will take a ruler and try to join point to point. That's not how we do it in physical science. You might do it in life science like that, where the variables aren't actually discrete points, or they're not a continuous thing. They're separate measurements, something like a patient's temperature or a plant's temperature over time. It can vary. It can be a broken line graph. But when we're doing it, even though it looks jagged, we take our ruler and we try and get a line that fits through the majority of the points, and it will look something like that. You'll see some of the points are not on the line. That one is slightly below, this one is slightly above. The difference between the line and where the point is, that can be measured as a bit of the error. Because in every experiment, there might be some error, human error or what we call experimental error. Now, we don't only get points that fit on a straight line. those are, you can use your ruler to see that it's a straight line. But you can also get points like this. Now I could say, well, the straight line looks like it could be somewhere over there, and we'll ignore those points. Or we could say we take the straight line like that. That's not the way to do it. You've got to look at the whole set of points as one big picture. And then you've got to draw a freehand line that fits through the majority of them. So to do this properly, we're going to erase all of those, and let's put the line in as accurately as we can. And I'm going to just do something like that. And although it's a little bit wobbly, with practice you'll get better, and make sure that you can see the shape of this graph looks a little bit like a parabola. Well, guys, I wish you well. You've got to practice in drawing graphs, and it is a very important idea, but there's so much more to learn about graphs. But first of all, let's go to a short break. Welcome back from that break. Let's get into the next skill that you need to know in terms of graphing. And I'll focus on showing relationships by using a graph. So previously, we've looked at plotting and the importance of plotting accurately. We're going to move on to talk about sketching and reading off values from graphs. Calculations in graphs, if you like. So how can we use these? And the first thing, that's quite an obvious one, is reading off values. Now, just like you plotted, sometimes you might be asked, what's the value at, say, 9 minutes? So if we count along the blocks, we'd recognize that's halfway there, and we go all the way up. We'd use a ruler to do this. I can't use a ruler, but we go up into the middle of that line, and then come all the way across, and you can now read the value at that point to show you exactly what's happening on the graph. So usually in a question, you're asked to plot the graph and then do some calculations or reading of values. We can also do some sketch graphs, which we'll come to in a few minutes. So that's the first thing. So please make sure you show how you've read off the values. So don't just read it off and write the answer down, but show it with dotted lines across the graph like I've done there. The next thing that we often have to do is the calculation of the gradient of a line. Now, we don't have to do the calculation of the gradient if it's not a straight line that is very clear and obvious in terms of the best fit curve or the best fit line. But calculating gradient is not something you can just do in your head. You have to show it on the graph. So again, if you've got a graph like this, how do we actually get the gradient sorted out? Now, the first thing you're going to do is you're going to look for a nice point that passes through some big lines. So they should be at the intersection of two of those big lines. And I've looked all the way along, and I don't see anywhere that this graph cuts through 2 points that are on exactly the intersection of two lines. There is one that links with two minor lines. So at that point, it cuts the graph cuts the axis or cuts the grid point that are clearly defined. They're not in the middle of the point. So I'm going to take that as 1 point, and I'm going to look now all the way along here to see if I can find another one that cuts through exactly at that sort of intersection point. Now, normally it isn't difficult to find, but this time it does look like it's a little bit more difficult. So I'm going to have to give up on that. I'm going to take that one over there like that. And the reason I'm taking that one is I want to show the biggest gradient. Don't just take gradients that are the biggest change. I don't want to take changes that are small. I want to show the gradient by looking at the big change. So if I've taken those 2 points, remember what the formula for gradient is. So it's going to be the change in distance over the change in time. And we're going to take this point here that we wrote up which has now disappeared, which was that point over there, as distance 2 minus distance 1 over time 2 minus time 1. Now, it's important, having looked at the points, that you actually write down those coordinates. So let's make sure that we've got that right. We recognize it's 14, 0.4, 0.8, 15.2, 15.6. And so that would be 15.6 on the time. So the axis is 15.6. And the dependent value is going to be 15.6 as well. So those 2 points, 15.6, 15.6, that is 0.2. What about 0.1? Well, 0.1 is all the way down here, and I'm going to just estimate that that's going to be about there, which is 2.4. And guess what? The value on this side is also 2.4. So we've now got to plug those values into that equation, and we're going to get the gradient calculation. So show the working on the graph, and you often do it in terms of the change in the one divided by the change in the other. So we're going to say this one is delta t, and this one is delta d, and we can put those values in. I'm not going to do the calculation, but you must show it on the graph. You must indicate what points you're using and do the calculation, and you'll see that it will come out that you can calculate the gradient quite easily. Now, that's one thing with calculation. The other thing with calculation is we sometimes need to remember we can calculate the area under the line or between the line and the horizontal axis. This doesn't only apply to motion graphs. Although the one I'm going to show you is a motion graph, please remember it doesn't only apply to motion graphs. It can be any graph. And that value has significance because the area under the graph is actually the independent variable multiplied by the dependent variable. And if that comes to a physical quantity, then that's what that area represents. So if we look at this graph, which shows velocity over a period of time, and it's a car traveling, we know that velocity times time is going to give you distance. So the area under this graph can be used to work out the displacement or the distance versus time graph. That little area is a triangle, and we would use the formula for the triangle as half base times height, and that calculation will actually give us the distance the object has moved in the first 2 seconds. And so as we carry on, we can then find the distance for the whole time of motion using that big triangle and do that sort of calculation. Sometimes the graphs can be a little bit more interesting. So for example, we can get one that looks like this. And what I need you to understand here is we've got a bit of a trapezium. So we can break it apart into a triangle there, a triangle there, and a triangle there. Below the line, this is a negative space. This is a positive because it's above the line. This is positive and this is a rectangle. And so you can work out the different areas using adding those together to get the total change in position or the total distance traveled. So it's very important that you can do this. Please remember, there is a short way. If you know the area of a trapezium, there is an equation for that, and it simply says take the length of this one, the length of that one, and add them together, and then take the height and multiply it. So the area of the trapezium is going to be the average, it's half of L1 plus L2 times the height. That will give you the area of the trapezium. Now remember, that's all positive. You've got to subtract the negative part of the triangle below. What does that negative mean? Well, we're going to talk a little bit about that now. So when you look at relationships, please remember that you check that you've got the graph and you understand the relationship between the variables. Include the headings and the labels when you're sketching a graph, because this can help us understand what's happening. And you only add in a point when you're sketching if it is a critical value. So if something changes, that's where you need to have it joined in. So let's have a look at a sketch graph that we might want to look at. So this is a distance versus time graph. And you'll see here I've accurately plotted the points. That's not a sketch graph, but it's giving you the shape of the distance time graph. And as I've drawn it before, I'm going to draw it again. You can see that's like a parabola. And if they ask us now to say, so what would the velocity versus time graph, or speed versus time graph, look like? And they asked you to sketch it. From this graph, sketch the other one. Well, there's a trick here. When you're doing that sort of calculation, what you've got to look at is the gradient. And the gradient over here is 0, and it's increasing positively. And it's getting bigger and bigger. So the sketch graph that we would do for velocity versus time over here would simply be a straight line like that. And if we were given a certain value, we could say, well, at 10 seconds, it was a particular velocity that we've been able to work out the gradient at that point. So that's a bit about sketching. Please make sure that you follow that very carefully. So guys, what we've done so far, we've done some plotting, we've done some sketching, and I think we've done a lot to enhance our skills on graphs. Welcome back from that break. We've been focusing on graphs, in particular, how to plot a graph and how to sketch a graph. These are important skills, but another very important skill is interpreting graphs. Let's go and have a look at what we need to do. So when we interpret graphs, it's about recognizing what the type of relationship is. And the type of relationship we can see based on the shape of the graph. So the shape of the graph gives us a very good indication of what's happening between the variables. And I want to remind you about the different types of relationship that are related to shape. So where do we begin? What's the most common graph that we come across in either physics or chemistry? Well, it's that one that has a straight line to it, that passes through the origin. Have a look here. So this graph, which is one that we've referred to before, a distance and time graph, you can see that even though some of the points aren't exactly on the line of best fit, it gives you a trend that is a straight line. It's not, can't be confused with some sort of funny curve. It's a straight line. And the straight line has a constant gradient. This means that this equation, the equation of this line, is in the form of y equals mx plus c. And that's the maths part of this lesson. But notice something about the y-intercept or the vertical intercept. It's equal to 0. So when c is equal to 0, we've got y equals mx. And guys, if we've got y equals mx, that means that whatever we do to x, we're multiplying x by a constant, and that will give you y. So the y divided by x is going to be a constant. That tells us that this relationship between these two variables is directly proportional. So that's an important word to remember, and it's an important feature to take note of, directly proportional. What it means is that if you increase the independent variable by a certain factor, then the dependent variable is going to increase by the same factor. As the one goes up, the other goes up, but by the same proportion. So if you double the one, you double the other. And that's what you can tell by looking at a graph with a straight line, but it must pass through the origin. Look at this one. So this graph, it's a straight line, but notice something about it. It doesn't pass through the origin. This is not directly proportional. It's not directly proportional. The gradient is constant, is equal to a number, it's a constant, but it doesn't mean that the relationship, if you double the one, you're not going to double the other, because in this type of graph, the equation of the graph is related to that full equation of y equals mx plus c, and the c factor stops it being totally proportional. So that's very important for you to understand, that when we've got these sort of relationships, the equations are going to look a little different. Whereas when it's directly proportional, like in the previous graph, what you're going to find is that in this graph, we can put it into an equation where we're going to say something like this, that velocity is equal to the change in distance over the change in time. And so we can manipulate that into an equation that actually makes sense and we can use to do some calculations. The two are related, and so I hope you've got that very clearly in terms of where we're going. So those ones had straight lines, but what happens when you get one that is a curve like this? So very clearly this is a curve, and it looks to me a bit like a parabola, or part of a parabola. Parabola. Sorry, my spelling's not very good, but we've got it. So I need you to understand something now, that if you see something that is like a parabola, even a quarter of a bit of a parabola, half a parabola, look and see it's going through the origin, and if we reflected this about that vertical axis, it would make a nice up-shaped, smiley-faced parabola. It would go right round like this. Now, it's a graph of kinetic energy against velocity. Now, you should know that kinetic energy is equal to half the mass times the velocity squared. And if you look at that, you'll see that it's really in the form of y equals ax squared, where this half m is equivalent to the a. So if we want to check, is it a parabola or is it maybe something similar to a parabola, what do? We've got to do another type of plot. Instead of plotting the y value, the kinetic energy against velocity, we're going to say, let's plot the velocity squared against the kinetic energy. Now, if we plot then this is going to be a constant. What do you predict if you do that? Well, it would be a straight line. And so we can see the relationship from the shape and from the axis. So looking at the axis, you'll see this is velocity squared, and this is EK. So we've got EK is directly proportional to velocity squared. Why would I say directly proportional? Well, look at it. Look at that pink line. It's a lovely pink line. It's going through the origin, and it is a straight line that's going through most of the points. So we can say kinetic energy is directly proportional to velocity squared because of the shape of the graph. And so what would the gradient be here? This gradient is going to be equal to half the mass of the object. And how did we get that? Well, we saw originally the equation is EK is equal to half m for mass v squared. So if we look at EK over over v squared, then you're left with half m on that side. So the gradient is a very particular thing, and we can write this in the form of y equals mx. And that's exactly what I'm doing here. So in the form of y equals mx, what I'm saying is that's my y, the EK is the y. The x is the v squared, and this part here is the m, which is the gradient. And so we can say, as I've written it over here, from this sort of graph, ek is directly proportional to the v squared. Now, what other sort of relationship have we got? We've got directly proportional, a squared relationship, and the last one, which is also very important, is an inverse proportionality. And so we're not going to make it too difficult, but let's have a look at an example just to show where we're at here. So the points here seem to make a bit of a curve, and I'm going to plot them like that and draw in the line that's kind of the line of best fit. And the question is, so is this a parabola, or what sort of graph is it? It's got a curve to it, but we're not really sure. And so there's a mathematical trick that we can use. Just one of the many tricks that physicists and chemists use to try and establish the relationship. So like we did in the other one, we plotted ek against v squared. Here we're not going to just take the graph of pressure against volume, but because we can see as the one is increasing, the volume is increasing, the other is decreasing. It looks like as the one goes up, the other one goes down. Let's rather take the reciprocal of the one. That means 1 over. So what I'm going to do is I'm going to take volume and I'm going to change it to 1 over volume. And if I do that, look what I've got. That -1 there represents the 1 over. That -3 represents that it's 1 over. And so here we've got the graph showing the pressure of a fixed mass of gas and the reciprocal of volume. It means 1 over volume. And so what we're saying in this graph is that pressure is directly proportional to 1 over volume. Notice it goes through the origin, and the gradient here is a constant. What do you think that gradient could represent or contain? Well, it would contain a factor that relates to the mass of the gas, and I also know that it could be related to the temperature of the gas at that particular point that we're measuring it. So the graphs tell us many things. The shapes and the relationships are determined, and we can interpret them. It's important to look at them and to see. But guys, these aren't the only things to look at. We do need to keep in mind this relationship between an equation, the graph, the shape, and the relationship. And I think that makes a lot of sense for us to make sure that we've covered the most important skills when it comes to interpreting and linking our interpreting to the relationships. Because the relationships that we've looked at, directly proportional, where the graph looks something like that, where this is going to be a value like distance, this one is time, this one, the squared relationship, where we had kinetic energy against V, and that was what the graph looked like, and then we changed it. We said it's the kinetic energy, which is Ek, plotted against V squared, and we found that it was a straight line. And finally, the inverse relationship, we had pressure against 1 over volume, and that was a straight line that passed through the origin. So please make sure that you understand these relationships. By looking at the shape, you're going to say, so what's happening as I change the one variable? What's happening to the other variable? I know that's been a lot to think about, and so you know what? I think you deserve a good break. So take a stretch, take a deep breath, have a drink of water, and we'll be back straight after this. Hello everyone, welcome back. We're looking at the importance of interpreting graphs. Now, there are lots of ways that an examiner or a teacher can ask questions about graphs, can ask questions about comparing graphs, all sorts of things where you can have to read off values and predict what's happening and make some deductions, but I thought that I would separate out some special features of graphs for us to look at, which will help our understanding not just of the relationships that the graphs tell us about, but how we can see what's happening as certain things change. So the first thing that I want us to look at is when you look at a graph, look and see what the maximum and minimum values are. Now, this isn't something that happens on every graph, but it is useful to see where the graph starts from and where it ends. The most important type of graph that we look at is particularly the linear graph, the straight line. And ask ourselves, does it start at the origin? Because you already know that if it starts at the origin, then it could possibly be directly proportional. And particularly if it's a straight line, then we know that it will be directly proportional. But it's not only where it starts from. So this one, we're looking at starting just on that side, but we're looking at the maximum value as well. And the maximum value over here is somewhere in that region there. I haven't put values on this axis, but I just wanted to show you that there's an important feature that happens when we get a curve like this. This is the graph showing the distance a ball travels when it's thrown up. So the ball starts on the ground next to where I am, and I'm going to throw it up into the air, and we're going to see how far it gets away from me and what's going to happen as it comes back down again. So it's about the distance that it's traveled, and what we can see, it's a kind of the distance above the ground. So this is the maximum height. And what I think is very important here is to recognize that initially, that when we look at this graph, we'll see that in one block of time, look, it's traveling more than 2 blocks of distance. And if we look at the next section for the next block of time, there's another block of time there, look how far it goes. It's not even going 2, it's going 1 and a bit. So what is this saying to you? It's traveling less and less in equal intervals. So it's often good to look at time intervals and say, what's the change within each time interval? And so if it's going less and less, what does that mean? It tells us that by looking at this, it is slowing down. Have a look if I'm correct. Take this time interval. Now it's the same time interval that we went more than 2 blocks. We'll start at this point and we'll end at that point. Can you see it hasn't even got a height or a distance traveled of 1 big block? It's a little section so it's going very, very slowly. It's getting slower and slower. So the other way to look at this is to say what's happening to the gradient of a line that is just touching the curve at one point. And I hope you can see, I'll just use my finger here or my hand. Over here it's quite steep. Over here it's less steep. Over here it's less steep. Over here it's less steep. And over here it is horizontal. In other words, at that point it's stopped moving. Just for a small interval of time, it's got to 0 velocity. So what I'm showing you on this graph is that the maximum value is at the highest point above the ground, and at that point the stone has, or the ball, what was it? A ball travels up. It has stopped moving upwards. It has got 0 velocity, and it's now changing direction and starting to move down. And that change in direction is very important because velocity is a vector quantity. So if we recognize something over here, you'll recognize when I put my hand like this, that line that is drawn as a tangent to this curve has got a positive gradient. But on this side, the gradient is negative. And notice over there it's flat, over there it's a bit steeper, and over here it's getting steeper still, and over there it's steeper. So it's getting bigger and bigger in the negative direction. And that means because it was going up was positive and down was negative, we have to recognize that as a vector quantity, there's been a change in direction. And so I hope you can see graphs give us a lot of information and tell us a story of what's happening to this ball that we threw up in the air. And from this graph, we could draw a secondary graph, which shows us that there's been a change in direction. So I'm going to draw a sketch graph over here just to link the two together. And the sketch graph that I'm going to draw is the sketch graph of the velocity versus the time. And if you notice, I started with a big velocity that was positive, and it decreased until 0, and then it's increased as it's gone further and further down. That's not very accurate. It should have been the same. It should have been symmetrical, but it gives you the idea. Whenever it crosses the axis, this time axis, that was the positive velocity, this is a negative velocity. It's changed direction. This point here, that point there, correlates to the highest point. So at the highest point, the stone has 0 velocity, but it has the maximum height above the ground. Okay, so I hope you can see there's lots to tell by just looking at key features like minimum points and maximum points. The other thing that is important as a feature of a graph is where there are horizontal lines. Where the object or the curve of the line flattens off and it becomes horizontal. Now, this is telling us something very important. So have a look at the example and we'll see exactly what's happening. So here I've misspelt. This was the volume measured in centimeters cubed. And we're just going to correct that. This is the time over which that happens. So if we've got a chemical reaction that's, for example, producing carbon dioxide, we could collect those bubbles of gas and measure the number of the volume against time. And so what do you see? Similar to in the first time interval, lots of bubbles. In the second time interval, okay, you can see here it was 2 and a bit. In the second time interval, it's just 1 and a bit. And in the third time interval, it's also 1 and a bit. So this section here seems to be fairly constant. And so we could say that is more or less a straight line. And we could measure that and call it the rate of the reaction, or the amount of gas collected per unit time. And it's happening at the same rate. But notice what's happening over here. It's slowing down. And even over there, it's slowing down. And over here, it's stopped. There's no increase or decrease in the volume of gas. So what's happened? The horizontal bit to the line tells us that this reaction has ended. The reaction has ended. And there's now a constant volume that's not changing, and we can read off the final volume of the gas that we've collected. So again, it's very important. Remember the shape, remember the minimum point, the maximum point, the steepness, and the change of the steepness over time, and when it becomes horizontal. Horizontal is telling you something. In this case, it tells you that the reaction is over. Now, let's look at another feature that we might need to focus on. We've said something about it already, and that's about crossing the horizontal axis. This is particularly important when we're dealing with vector quantities, because remember what a vector quantity is. It's something that has magnitude and direction. And we can indicate that direction as being, for example, positive or negative. So in the graph, when a value crosses the horizontal axis, then there's been a change in direction. So have a look at this graph. We've seen one like this before. What's it telling us? Because we've got a number of features. Notice this one is telling us that this is increasing velocity. So the velocity originally was 0, and it's getting, in time, it's getting more and more and more. But notice that these are the same sort of increases. So it's a constant increase. So it's not just getting faster and faster, it's getting faster and faster by the same amount. That's what this straight line indicates. Very important to see that. But now what is this saying? The velocity now, it's gone to horizontal. Is that saying it's over, that it's stopped? No. What it's telling us, that it has a constant velocity. So if this was 20, as an example, at that time, it's still 20 at that time, it's still 20 at that time, still 20 at that time. It's just not getting faster. It's not slowing down, and it's not speeding up. It has become constant. So just like the volume became constant, this illustrates the constant velocity. Now, what happens if we get a negative gradient? Well, what's happening to the velocity? Over here it was 20, over here it's got less, and it's now increasing in the negative direction. So as we go down here, we can say it's slowing down. But over here, it's speeding up. And what's the difference? It's crossed the axis. So it's gone forward, slowing down, turned around and moved back in the opposite direction. So it's very important to see that. Slowed down, got to zero, moved in the opposite direction to what it originally was. So it's kind of reversing. And that's what happens when we cross the axis. Okay, guys, I hope this has helped us to look at graphs, to sketch them, to draw them accurately, to extract information from them, and also to interpret the features of the graphs so we can have a link between the graphs and the relationships that we're investigating. It's been a lot of fun being with you today, and so I'm going to say goodbye, and we'll see you again soon.